We will talk about various different properties of a pointers. Remember, a pointer is a data type. When declared on the stack, a pointer variable is used to store memory addresses. In C and C++, both compilers provide us with a series of derived pointer types. And these are char, start, integer, start, string, start, etc. And when you do a size of, meaning when you print out the size of each of these pointer types, you'll get a number back. On a 32-bit computer, that pointer size is generally 4 bytes, whereas on the 64-bit computer, that size is generally 8 bytes. You can run this on an IDE and see for yourself. Remember, when a variable is declared on the stack, such as when you have an integer variable, this integer is of 4 bytes. However, if you're to declare a pointer type that points to an integer, that's what we call an integer pointer. This integer pointer takes up 8 bytes. So run it on your computer and see what you get. Let's quickly run this on an IDE. Let's print out the size of an integer. And when we run this, we see on a 64-bit computer, we get 4 bytes. If we change this to a pointer type, integer start, meaning the pointer pointing to an integer, we get 8 bytes. Let's go back to our slides. Notice that depending on your compiler, C or C++, the size of function is not always the same. It varies from architecture to architecture. So if you have a very old C or C++ compiler, you may be getting a lot less in your variable size or pointer size. Let's move on to the next one to talk a bit more about pointers. To illustrate, let's go through these examples from top to bottom. Let's declare 2 integers, x and y, each with a value 1 and 2 respectively. And then we declare a pointer variable, and this is an integer pointer called p. This p occupies 8 bytes of memory on the stack, whereas both x and y 4 bytes each. Then we assign the address of x to p. Right after it, we then assign the address of y to p. This is permissible because pointers can be reassigned. So in general, you can keep on reassigning values to pointer as long as the pointer variable is not declared as a const. You can also assign a pointer to an initial value of null pointer. This is the type-safe way of representing null, N-U-L-L, with a value of 0. This means that this pointer has a label null. It is not pointing to anything else. This is a default label for initializing any pointers. Let's illustrate all of this here. Let's say you have a memory cloud. Your both x and y are occupying certain spaces inside this memory cloud on the stack. And both x and y have different memory addresses associated with them. So is p, which is a pointer data type that sits somewhere else, also on the stack. We assigned a value to p. That value is the address of x. So whatever that address is becomes the value of p. And then we assign the address of y to p, overriding the previous value, which is the address of x. After all said and done, we nullify everything, assigning a null value to p and ULL. That's it. In the next line, we're creating a reference variable, r. This reference variable is an alias of x, which means r refers to the same memory address where x is. Both r and x are of the same variable. And this is absolutely allowed. As we stated before, when you create a reference variable in C or C++, you must initialize it with a value, in this case, x. If you had done this instead by creating a reference variable without initializing it to a variable on the stack or even from the heap, this will not work in C and C++. Your compiler is not going to compile it. Similarly, you cannot create a reference variable and assigning it to a null value. This is not allowed. Therefore, when initializing a reference variable, you must initialize it with a valid variable of a known data type that occupies a certain amount of memory. This is the reason why we said reference has to be initialized upon declarations. Once initialized, a reference cannot be reassigned. Therefore, when you create a reference variable pointing to X, you cannot later reassign this R to another variable on the stack. Let's look at the next slide. In the previous slide, we saw that we can create C++ references that allows you to create a second name for a variable that you can use to read or modify the original data stored in that variable. This allows you to treat the reference variable exactly as though it were the original variable for the purpose of accessing and modifying the value of the original variable, even if the second name is located within a different scope. We start with declaring a variable of integer type with a value of 1, and then we create an alias of that X, and this alias variable is Y. Now let's look at this example. Forget about the external keywords here. In this example, your compiler is going to give you an error, and this error is pretty obvious. In order for reference to work, you must declare it with a valid object, which means that the right-hand side must be a L value, which means in computer science, a memory location which identifies an object, such as in the example of above, where X occupies a valid memory address, and it is also a valid object. You can't simply have 1 here and use it to initialize your reference variable, because 1 is a constant value. In computer science, this is what we call R value, which does not refer to a memory location that identifies an object. Another way of thinking about it is an R value simply refers to data value that is stored at some address in memory. So this data value cannot be used to initialize your reference. You must use an L value to initialize your reference, Z. Let's look at some of the other examples. You can also have a function that returns a reference variable, as well as the parameter inside the function that uses a reference variable. In both instances, this reference variable refers to the original variable that this reference variable is initialized with. You may call these reference variables reference to whatever the type that they're referencing. In this case, integer ampersand would be reference to in. Chart ampersand would be reference to char. String ampersand will be reference to string, so on and so forth. Let's look at this example in yellow. We have 2 statements here. The first one is declarations of a char variable with a value of A. The second statement is a declaration of pointer variable, C pointer, that points to a char. C pointer is not initialized. Inside your memory address, C occupies F120, C pointer occupies F121. The memory addresses of these variables could be different. They don't have to be incremented from each other. Inside this memory address F120, we see a value of 65. 65 is the ASCII value of your character, capitalized A. In binary, this would be 0100-0001. C pointer, on the other hand, is what we call undefined. Therefore, we put question marks here. Undefined meaning at this memory location, there could be any data sitting inside of it. It could be 1, -2, 2000, 3000. We don't know what it is because we have not initialized it with a valid data value. So let's fill this out. C is a variable of type char. When C is declared, the computer allocates 1 byte to it. The reason why C is 1 byte is because the size of char gives 1. C is then assigned a value of 65 or A to it. 65 corresponds to this value in binary. This memory is allocated on the stack. C as well as C pointers are allocated on stack. C pointer is then allocated enough memory in computer to hold a memory address for a char. So when we do size of C pointer on your 64-bit computer, you should be getting an 8, which is 8 bytes. And there's nothing assigned to C pointers yet. This completes the discussions of some of the properties associated with the pointers and references in C and C++.